All right, guys, so welcome back to part B of Lab 1. And we are in the middle of slide 15, or we're about to start at slide 15. So here I wanted to give you the basic breakdown of a for loop. And now we can tackle what's going on in that slide. So in this example, we're using a for loop and we're directly using the iterator I to do something, right? To do something. But we don't necessarily, it's not the only thing we can use when we're iterating through a for loop. For example, the first for loop that I'm doing right here. In the first for loop, I'm creating a vector A. And as you can see, vector A is going to be what? A vector of size 10, from 10 going to 1. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And I'm creating another data container that's simply CNT equals 1. That basically stands for count. And then we jump into the for loop from lines 4 to 8. So what I'm going to do first, I'm going to copy this and run this so you guys can see it. Oh, let's see. Let's see how bad it is if I copy it. Oh, that's not bad. I'll clean that up. Alrighty. Process this line, process that line. And as you can see, after we process those lines, we have an A container and a CNT container. And then I'll run this line right here. Right. Actually, first, let's view what A is. 10, 9, 8, 7, 6, 5, 4, 3, 1. Now I will run this. And now A will have these values, and CNT will have this last value of 11. Okay, why? Well, here, if we jump ahead to the slide, it starts off like this. A is 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And CNT is 1. On the first loop, wall takes in the value what? And by the way, notice I chose a ridiculous, I don't know what the hell wall is supposed to mean, but I'm trying to stress the fact that to the left of the end, the iterator can be it's a variable and it can be named anything you want, depending on the code you're doing. So in this example, there's going to be obviously 10 loops. Why? Because A has 10 elements, right? And the iterator, that is wall, is going to iterate through each one of them in every iteration of the loop. So that means there'll be 10 loops. All right, and on the first loop, wall is going to have the value, the original value in A, which is 10. All right, which is going to be 10. Now, this is important. We are iterating. Let me scroll down a little bit so you can see both simultaneously. We are iterating through A, and we are also in the code changing the values of A. In a situation like that, wall will iterate through the original values of A. It doesn't matter how we're changing it in the for loop. What happens is when the for loop starts, wall takes a snapshot of what's in A, and it will run through those original iterations. It does not matter that we're changing A. It will run through the original values of A. So the first value of A is 10. Wall takes on the value of 10. And CNT, as we know, has a value 1. Okay, has a value 1. Armed with that information, we jump down here into the code, line 70. Okay, what's going on here? Remember, there's a single equals here. That means we are either creating or transforming. We do the right side first and the left side first. The right side is saying wall plus 5. Wall plus 5. Vector mathematics are in play. What is wall? In this case, wall is easy. Wall is just a single value. Wall is 10. 10 plus 5 is going to be 15. Excellent. So the right side is 15. Now on the left side, it's saying A bracket C and T. All right? A bracket CNT. Now, you have seen so far how we put we have put a number in between those brackets. This is the first time you're seeing a variable within the brackets, but it means the same thing. What is the value of CNT? Well, the value of CNT currently is 1. So this reduces to A of 1. A bracket, A open bracket 1, close bracket. A of 1. So this becomes A of 1 equals 15. So the first value of A is now being set to 15. Done. And that is why over here, the 10 and this part now is overwritten to be 15. That's what has happened. And then we're not done in line 71, the second line. We're doing this line of code. And again, you might get a little confused because you see a CNT here and you see a CNT here, right? A lot of comp sci 111 people, when they take comp sci 111, the first time they see that, they're like, what is going on? Again, you have a single equals here. That means there's an order of operations. Which side goes first? The right side. What is CNT plus 1? Well, first of all, what is CNT right now? As of now, CNT is the value 1. What is 1 plus 1? 2. So this right side is basically 2, reduces to 2. The left side now just simply becomes CNT equals 2. Done. CNT equals 2. So now CNT has been incremented to be 2, and that's why. And now we come down here, the first loop is ended, and now we go on to the next loop. Wall now takes on the next original value of A, which is 9. And in that situation, wall is now 9, CNT is now 2. CNT is now 2. And so now when you go to the code down here, it is now 9 plus 5, which is 14. And 14 now equals A of 2. A of 2. So now the second value of A is going to take on the value of 14. And that's where that comes from. That's where that comes from. Sorry. And now we come down here, and now it's going to be 2 plus 1, which is now 3, is going to be equal to CNT. CNT gets overwritten again to be 3, right? At this point, CNT equals 3. We come down here to the end of the loop, and then we must enter the third loop where wall takes on the value, the third value of A, which is 8. Which is 8. And that's why in loop 3, when we start off loop 3, wall has a value 8, CNT has the value 3. And what ends up happening is now the third value gets overwritten to be, oh, did I jump the gun? Oh, right here, the third value gets overwritten to be 13. And then we go into loop 4, right? Loop 4, CNT is going to have the value 4. Wall is going to have the value 5. 7 plus 5 is going to be 7 plus 5 will be 12. And that'll go into the fourth position of array. In loop 5, wall's going to have a value 6. 6 plus 5 is going to be 11. That's going to go in the fifth position of A. In loop 6, wall's going to have a value of 5. And then the sixth value is going to be 5 plus 5, which is 10, and that's why 10 goes in the sixth position, and so on, so on, so on. I go up to all the way up to loop 7. I show you how it's changing, right? But this will go all the way up to 10 loops. It'll go all the way to 10 loops, and it'll change the values so that A finally gets transformed to this. So basically what happens is, what do we end up doing? We ended up adding 5 to all the original values of A, right? We had ended up adding 5 to all the original values of A. All right, so that is basically a for loop. And now I wanted to show you some nifty little functions we have. We tend to use them with for loops, or we tend to use them individually, it doesn't matter. There's two new functions I'm going to show you that come in really handy. All caps and row, and the function length. So what do both these functions do? Well, they basically tell you how many elements there are in A. So right here, if I do n row A, it gives me 10 because there are A is of size 10. It's basically what's the bookshelf, what is the size of the bookshelf, how many values there are in the bookshelf. So there it gives you the value 10. And length, A, does the same thing. All right, this is for a single dimension vector. They'll do the same thing. It's not until we deal with tables that we'll get different results. All right, and when we get to tables, I'll bring up that point. But for vectors, they do the same thing. They give you the size of the vector. All right, so let's come down here now, and let's do this example right here. So V is now going to equal this monstrosity right here. Now you're going to see this. You're going to see situations where when we have the single equals, which implies that we're making or transforming a data container, a lot of complexity on both sides of the equals. It does not matter. You simply just reduce it to what's happening. All right? You'd reduce it to what's happening. So here we have 1 colon something. Now we do know 1 colon a number creates a vector from the first number to the second number, right? So here it looks like we have 1 to something. Well, this something represents a number. In this case, it represents the number 10 because n row of A by itself gives me 10. So then together, this is going to be 1 colon 10. Therefore, V is going to be the vector 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is what's going on there. Boom. And that's why V becomes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That easy. All right, and we could make this even fancier. Hypothetically, let's create a vector v2. Let's mess around with it a little more. Let's put a parenthesis in here and do like -3, right? What do you guys think is going to happen now? It's going to be 1 colon, and whatever this, oh, sorry, not equals 3, I apologize, -3. It's going to be 1 colon, whatever this is, right? So what is this? Well, n row of A is still 10. 10 minus 3 is 7. And this then will become 1 colon 7. Therefore, V2 will be 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Right? Boom. All right. So back to our original example. So we have our V, and now we have this for loop right here. Let me copy this. Clean that up. Alrighty. So here we go for Joey and V. So Joey is going to be the iterator. It's going to iterate through the vector V, not V2. Let me type in V down here again. Right? V has 10 elements. Therefore, this for loop will run 10 times. And it looks like in each iteration, it's going to change the values of A. We already have A. In this case, it's 15. It's these values right here. So notice now we are iterating through one vector and we're changing another. Again, that's fine. And for loops, they're used for all kinds of things. They're all kinds of things. So in this case, Joey will take on the first value of Joey will be 1. This will turn into A of 1 equals, remember, we have A of Joey on both sides. It does not matter. When you have a single equal, you do the right side first and the left side. The right side gets reduced, then you hit up the left side. So A of 1, Joey's 1, A of 1 plus 5. What is A of 1? A of 1 is 15. 15 plus 5 is 20. So the right side of equals is basically has the number 20 in this particular iteration. The left side is saying A of 1 equals 20, right? So now the first value of A will become 20. On the next iteration, the second loop, Joey will take on the value of 2. And then again, down here, it'll become A of 2 equals 14 plus 5, which is 19. So so the second value of A will be overwritten to be 19. And so on, and so on, and so on. If I run this whole for loop right here, A will basically be overwritten to be incremented by 5 again. Okay? So we just did it 2 different ways, but you see it in action. You see it in action, how we did it. All right? So it's really good to go do these particular examples with pencil and paper to give you some practice, just like with the practice set. So that's basically what the for loop is. All right? Now the for loop, go down here, tend to be used in together with they tend to be used together with the if-else statement, and that's what you see here. That's what you see here. I have a slight typo here because else right here should be on the same line as the closing bracket of the if. So what I'm going to do is I'm going to rewrite this in R just so you guys can see it clearer. So basically we start off with this original vector of b equals 1 colon 5. Right, let me just copy and paste all this. Oh, just let me copy it nice and easy. Right. Scroll down a little bit so you can see it. I'm going to clean this up a little bit. All right. Equals 5. And here you go. So now we have basically the right, oh, let me move this up. But right now I'm not getting an error. But most of the time, sometimes it gives you the else gives you an error, sometimes it doesn't, depending on the syntax. So it looks like it works fine here. Just to be on the safe side though, some versions of R require you to put the else like that. So if, close the bracket, and then the else on the same line as a closed bracket of if, and like this. So it looks like right now both ways are working. Again, it depends on the latest version of R. Looks like they changed that, which is good. You should have the flexibility to write if else the way you want. So if you're not getting a typo, that's fine. If you are getting a typo, that's usually where the else is. That's usually the case. They want you to put the else on the closing bracket. R needs to make up its mind in this situation. So anyway, we ran this, and what's happening here? Okay, what is happening here? So for this, I'm going to do this by hand. I will do this by hand to show you guys what's going on. And what I'm going to do is I'm going to open up an Excel sheet and do it for you side by side. All right, it shouldn't take too long because B is just 5 elements and we're iterating through B, so it won't be that big a deal. So let me minimize this. Okay, perfect. All right. And now to its side, guys. All right, so we start off with B. So what is B? Can you guys see this? Can I slightly zoom in a little bit more? All right, so B is a vector that's going to be 1, 2, 3, 4, 5, right? So that's going to be B. And now we're going to have a variable Janice that's going to iterate through. Look what I did there. Look what I did. To the right of in, I gave not a simple vector, but I gave some sort of logic, right? And so that's one of the things I wanted to show you guys, that to the right of in, we give a vector, but it doesn't have to be explicit. It could be something that is dynamically generated, a vector that's dynamically generated at that moment. So like before, everything else in R, just minimize it at that moment. So what is one colon n row B? 1 colon n row B is basically going to be, well, what is n row B? N row B is basically how many elements there are in B. How many elements are there in B, guys? 5. So that's basically going to minimize to 1 colon 5. Oops. It's going to basically turn into Janice in 1 colon 5, right? Janice, Janik. For some reason I wrote Janik. Janice in 1 colon 5. So Janice is going to iterate through what values? 1, 2, 3, 4, 5. In this case, you're wondering, well, what the hell did I do 1 colon n row B? I should have just left it B. Yeah, here, that you're absolutely correct. I just wanted to show you guys this, right? So there'll be 5 loops because Janice is iterating through 5 values, 1 colon 5, which is 1, 2, 3, 4, 5. And let's just jump into it. So loop 1, Janice takes on the value 1. It's the first value. All right, Janice is 1. Now, when you jump into the code, we have this whole if-else thing. The if-else works the same way that it would work outside the for loop, right? Outside the for loop. So we go first to line 91, and we test the logic. Is B of Janice less than 3? Is B of Janice less than 3? Okay, B of Janice is less than 3. Basically, it's asking, is B of what? 1, because Janice is 1. Is B of 1 less than 3? What is the first value of B? The first value of B is 1. We go up here, the first value of B is 1. Is 1 less than 3? It is. This statement is true. For the first loop, this statement is true. Therefore, I will ignore this. This does not exist for me anymore, and I will execute this. What does this become? This becomes B of 1 equals B of 1 plus 5. Now, we've done this before. We do the right side first. What is the right side? The right side is B of 1, which is 1, the first value of B, plus 5. So 1 plus 5 is 6. So the first value of B is overwritten to be 6. So I will come up here, and I will take this and overwrite this to now be 6. Done. All right. We are now done with the first loop, because remember, if else is only one of the actions, only one of the codes in the brackets can happen. So we're done with the first iteration of the loop. We now move into loop 2. All right, and in loop 2, Janice now has the value 2. Sorry. Okay, now we go down to the logic again here. If B of 2, basically it's asking in line 91, is B of 2 less than 3? Well, what is the second value of B, ladies and gentlemen? It is 2. Is 2 less than 3? It is. It's true. Therefore, I will execute this line of code again, and I will ignore everything in the else. From bracket 95 to 97, it'll be ignored. So this again becomes b of 2 equals b of 2 plus 5. All right. What is b of, on the right side again, what is b of 2? b of 2 is 2. 2 plus 5 is 7. Therefore, the second value of b is not going to transform into 7. Done. All right. We're done with that. Now we jump into loop 3. Janice now has the value of 3. All right. And now we have to test the question again. Is b of 3 less than 3? Right, so what's the third value of b? It's 3. Is 3 less than 3? It is not. This statement is false. Basically, this condition right here is false. Therefore, now we ignore this, and now we jump to else. And now we do the else part. So else here will now become reduced to b of 3 equals b of 3 minus 5, right? And so the right side is third value of b is 3. 3 minus 5 is negative 2. So the third value of b becomes negative 2. Loop 4. The fourth value of loop of 4 becomes Janice equals 4. And line 91, we're testing the condition is b of 4 going to be less than 3. What is the fourth value of b here, ladies and gentlemen? It's 4. Is 4 less than 3? It's not. It's false. So then we come down here and do the line 96 again, which is going to be, I'm going to cheat a little bit, copy this. This will become b of 4 equals b of 4 minus 5, and that becomes negative 1. And finally, we jump to loop 5. Janice now equals 5. Janice now equals 5. And this now asks the question, is b of 5 less than 3? And that becomes now, again, line 96. I'll overwrite this again. And this becomes b of 5 equals b of 5 minus 5. So this now, the fifth value now becomes 0. Right? And now we're finally done with all the 5 iterations of the for loop. And once we're finally done, b has now transformed into the values 6, 7, negative 2, negative 1, and 0. Right? And now, maximize this so you can see this. And now if we run this, type in b down here, you can see that the value is indeed 6, 7, negative 2, negative 1, and 0. Right there. And that's basically how for loops and if-else statements are used in tandem. You'll see more of this. Now, I taught you guys for loops and if-else statements because I need to teach you guys for loops and if-else statements. We do use them very sparingly because this is R. And in R, we avoid for loops and if-else statements. Why? Because we use vector mathematics and vector logic. Vector mathematics and vector logic. So after I showed you all that, now I show you how to avoid it. Right? But this shows you the speed and power of R. There's other ways to do the same logic using those for loops faster and with less code. And this is what we call the whole vectorization and vector mathematics. And this is basically one of the things that was ripped off by NumPy in Python. And this is exactly why Python took off in the workforce in corporate America, because now you had the same features as R, but you had it in Python, which is actually a real programming language. You could build applications with Python. And in Python, it was actually faster. It was actually faster until they made something called data tables in R, which ripped off pandas. And in some cases, I've heard some people have argued the point that data tables is faster in some cases than pandas. Either way, data tables is an industry standard if you're using R, and that's what we'll be using for this class. That's what we'll be using for this class as well. All right, but for now, let me show you what I mean by the vector mathematics. So in line 1 over here, we create a vector 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, right? And here in line 4, I do something very bold. I simply do right, so I have this new A, it's 10, 4, 5, 6, 7, 3, 1, and I do A equals A plus 5. What the heck is this, ladies and gentlemen? What is going on? This is vector mathematics. All right. So look, we have a single equals here. We do the right side first. All right. And the right side, I have A plus 5. Okay. Now, if A was a single value, for example, let's say A was equal to 10. That would be no problem. That would be 10 plus 5 is 15. What the hell am I supposed to do with a vector? Same concept. In R, it sees you're adding a 5 to a data container, which is A. Or if you want to think about it, like a bookshelf. You're taking a value 5, you're adding it to the whole bookshelf. How does R interpret this? It's like, aha, I understand. It takes that 5 and then adds it to every element in A, or every data in every position in A. So what happens here is, here's A right now. 5 gets added to 10, gets added to 9, gets added to 8, 7, 6, 5, 4, all the way down. Then, so what happens is temporarily on the right side, there is a temporary array being created in memory, which is this. Then it does the left side, where it says, listen, A now equals this temporary array that's in memory. So when we execute this code, A is now overwritten to be that new array, and now A is this. Look what we just did. We just added 5 to every number like we did before using the for loop, except there's no for loop. We just directly did it to the container, and the container did it for us. Not only is this simpler, but this is faster. This is also faster. You don't notice the speed here, but when you're dealing with hundreds of thousands of rows, million rows, it's faster and more efficient. This is wild in R. This is wild in R. And also, obviously, in NumPy, vector mathematics is also optimized to be faster than for loops. So I did no for loops, and I have the same results. Let's take this a step further. Right? So here, we have B equals 1 colon 5, right? And then I do this right here, this logic. What is this? What's going on here? Let me show you. So B equals 1 colon 5, right? So B is 1, 2, 3, 4, 5. And then I do B is less than 3. What is that? And now you see these true, true, falses come out. What's going on here? Same logic as before. This time I'm doing, instead of math is happening, it's doing some sort of conditional check. So B is 1, 2, 3, 4, 5. And then I say, okay, then I say B less than 3. What the hell is going on there? What is R? How does R interpret this? R is like, I understand. You want to check to see if every element in B is less than 3. That's why you have this true, true, false, false. By the way, anybody new to programming, These are special kind of variables called Boolean variables. Boolean variables are not text. They're literally logical statements that are either true or false, and that's what it's saying. This is a Boolean is a unique thing. It's not a number, and it's not text. It's basically just true and false statements. True and false statements. So this is true, true, false, false. Why? Because 1 is less than 3. True. 2 is less than 3. True. 3 is not, false, and so on. And so on. Again, that's vector logic coming into play. All right, and we'll come back to this. We're going to actually use this logic to do something called logical slicing, which is very cool and very powerful. So now we get to these 2 points here. What's going on here? Ladies and gentlemen, a large part of data analysis is summarizing and transforming data, right? In our case, we have simple vectors we're using, but nevertheless, how do we take a subselection of those vectors? You saw before how I can simply choose one value at a time from a data container. But what if I want to choose multiple values? Or, to use my bookshelf analogy, what if I want to see the values, what's in the shelves, at several shelves? Let's say I have a bookshelf, I have 100 shelves in a bookshelf. I don't want to see one at a time. I don't want to see all 100. But I want to see a couple of them. I want to see a subset of that bookshelf. In this case, I want to see a subset of the vector, a subset of array. How do I do it? I'd use what we call a concept called slicing. And there's 2 ways to do slicing. Actually, there's 3 ways to do slicing in R, same way as in NumPy. The first way is to use the colon methodology, right? To use the colon methodology. So here I have B, again I have B, which is 1, 2, 3, 4, 5. Oh, sorry. 1, 2, 3, 4, 5. If I were to type in B bracket 1 colon 3, what's going on here? Well, this can get a little confusing because you're like, wait, 1 colon 3 is a vector. It's a vector 1, 2, 3. And you'd be correct. You're calling a vector inside these square brackets. But once you figure out that 1 colon 3 is 1, 2, 3, the same logic applies within the square brackets. When you're inside the square brackets, you're simply selecting which values you would like to see. In this case, I'm saying I would like to see the first value, the second value, and the third value. Boom. So this gave me the subset of B, which is the first and second and third value. Right? That's what's happening basically. That's what's happening. Yes, you are calling a vector with inside those brackets, but once you have a vector of numbers, those vector of numbers are now translate into or simplify into the positions that you want within B. And so with colon slicing, it is a great way to select a subset of data where the data is contiguous. It's all right next to one another. Right? It's all right next to one another. So I can do B1 colon 3. I can do B2 colon 4, which gives me 2, 3, 4. I can do, and let me mess around with this, by the way. Let me change this around. Let me do D equals 5 colon 1, so it's easier for you guys to see this. So let's say D now is 5, 4, 3, 2, 1, right? So if I did D1 colon 2, which values am I going to get? I'm going to get 5 and 4. I did this so you guys can see the difference between positions and values. So the first and second position of D gives me the 5 and 4 value because 5 and 4 are the first 2 values of D. If I were to do D 4 colon 5, I would then get 2 and 1. If I were to do 4 colon 3, what do I get? Yes, right. I get 2 and 3. Why? Because, type this in right here, because the fourth value of D is 2. The third value of D is 3. And that's why I got the result back as 2 and 3. because I said, hey, give me the fourth value first, and then give me the third value. And so that's how I get the subset of value from D. I get it in that order because I designated it in that order. Yep, you have that control. You have that control. So that is colon slicing. And by the way, hypothetically, if I were to do, let's say I did 3:10. Now, notice D only has five positions. What's going to happen in this case, guys? Am I going to get an error? I do not. It simply goes, give me the third value, which is 3. Give me the fourth value, which is 2. Give me the fifth value, which is 1. And then it goes to the sixth value. There is no sixth value, NA. Seventh value, no seventh value, NA. Eighth value, 9, 9 value, 10 value, NAs. Remember, in R, in the world of R, NAs are null as opposed to pandas and numpy, it's NaN, right? So that's what happens. You don't get an error. You do get a whole bunch of NAs back, though. Again, R is very flexible, and this goes back to the fact that R is again the basic building block of R is a vector. The basic building block of R is always a vector. So that's why there's always this flexibility. Okay? Alrighty. So that's colon slicing. All right. Now, what happens if you want to take a subset of, let's go back to B. Let's stick with D. Let's do B. We'll do B and D together. So what happens if we want to get a subset of a vector, but the values are not next to one another? How do we do that? All right. How do we do that? So let's say in the cases of B, I want the first and last value. Right? The first, whatever is the first and the last value in B. How would I do it? Okay. So basically, if you think about the colon logic creates a vector of numbers within the brackets that designates which position values we want. How would I do that in a situation where the numbers are not next to one another? You guys remember the C function? Right? This creates a vector 1, 5. So I need to put that vector basically in here. And now this vector becomes 1, 1, and 5. So what happens within B is this basically then says, okay, give me the values in the first and the fifth position of B. And that's how I get the 1, 5. So let's run this back with D. Right, if I want the first and last values of D, right, remember now D is 5, 4, 3, 2, 1. So if I want the first and last values of D, boom, I get 5 and 1. I get 5 and 1. Do you see that? Right? That's how you do slicing. That's non-contiguous. When you have slices, when you have values that aren't necessarily next to one another, just like in a bookshelf, you want the first book, you want the third book or the fifth book. This is how you do it. Use the C function. I told you you'd be using the C function all over the place. Use the C function. And so in this example right here, this y here, B is now BC parentheses 1 colon 4. You're basically calling for the first value and the fourth value in B, which gives you the answer 1 and 4. It gives the answer 1 and 4. So that's how the C function works. And remember, right, these, within the brackets, those vectors can become very complicated. So I can hypothetically do this. Just like if you remember our example from a few slides ago, where we used the C function to create one giant vector. So I can have a situation where I say, okay, C1 colon 2, 3, comma 5, right? And what does this reduce to? This becomes 1 and 2. Let's get a little more fancy. comma 5, right, something like this. So what is reduced to? This becomes 2, 1, comma 3, comma 5, right? So this within here, within the bracket, becomes a vector 2, 1, 2, comma 1, comma 3, comma 5, right? When it's placed within the square brackets, you're basically saying, hey, for D, give me the second value, the first value, the third value, and the fifth value in that order. And this is why you get something like this: 4, 5, 3, 2, 1. 4 is the second value, 5 is the first value, 3 is the third value, and 1 is the last value, the fifth value. And that's why you get those values back. First of all, those are the values you get back, and that's why you get them back in that order: 4, 5, 3, 2, 1. So it can get quite complex and complex to serve whatever needs you have. So that's the second type of slicing. And now we get to the fifth slice. I'm sorry, fifth. The third part, the third type of slicing, which is the logical slicing, right? Logical slicing. And this is by far the most powerful one. Right, the most powerful one. Let's break it down what's happening here, and then I'll do the example with, I'll run the example with D, okay? So here, a lot of things are going on here. A lot of things are going on. Recall from up here, our example up here. We can check a condition. We can check a condition for every value in a data container. And we get back true and false. That's what we call Booleans. Again, Booleans. All right? What were to happen if we replace those Booleans, all right? What would happen if we place those Booleans back within the square brackets of that data container? What would happen? Okay, what would happen? What happens is you're going to be doing Boolean slicing or logical slicing. You are choosing only the values that will be true. You are not choosing the values that are false, right? This is equivalent to if I had a bookshelf and I asked the question, show me just the shelves that have books that are the color red. Okay? So then it goes shelf by shelf, checking to see, is this book red? No. Is this book red? Yes. Is this book red? No. Is this book red? Yes. And it only gives you back the rows or the shelves with those books that meet the criteria. That is what's happening here. All right? So it's only giving back the B's values that meet this criteria in here. So if B is 1, 2, 3, 4, 5, as we know it is up here, B less than 3 will give me true, true, false, false, false. Only the first two are true. Therefore, this right here will give me the results 1 and 2. Ta-da. That's the subset you get. You get back just 1 and 2. To this 1 and 2, I'm adding plus 5. See that? I'm adding 5 to whatever this is. Well, this is a subset of B, which is just 1 and 2. So when I add 5 to it, I'm going to do it step by step. I now get back the results 6 and 7. Because this part right here is simply going to give me a subset of the vector, which is 1 and 2. That subset is going to be added to 5, vector mathematics, which now gives me a vector of two values, 6 and 7. All right, 6 and 7. And now that's 6 and 7, so this becomes basically 6 and 7. That 6 and 7 is now being set equal to this on the left side. Now you haven't seen this before. I have a 6 and a 7 on my right side of the equals, and on my left side now what happens is I am basically going to choose the positions that those 6 and 7 go to. Okay, so on the left side of the equals, right, which goes first, by the way, we are identifying the values that will overwrite the left side positions. On the left side, you're designating the positions that those values on the right side of the equals will go to. So here, b less than b equal 3, right, I'm figuring out which values I'm going to overwrite. Which values will I overwrite, ladies and gentlemen? I will overwrite, I go back to my original b, which is 1, 2, 3, 4, 5, and I look at all the conditions where b is less than 3. Well, b is less than 3 for the first value and second value, and that's it, right? So within b, I'm going to place these values, which is 6 and 7, in places where this is true, and it will happen in order from left to right. So what ends up happening here is, let me go to my little Excel page right here, just so I can show you. So right now, b is right, and on the right side, we have that is original b. We have this subset that is 6 and 7. Right, this right side is 6 and 7. Okay, but the only ones that are true, that are conditioned true on the left side of equals, right, on the left side of the equals, is going to be this value, because this value is indeed less than 3, and this value, which is less than 3. So these two values will be overwritten to these values. How will that happen? It goes literally left to right. So the first position that needs to be overwritten is 1. Therefore, 6 will go to 1. The second value that needs to be overwritten is the 2. Therefore, 7 will go to 2. And therefore, when everything is said and done, b will then become 6, 7, 3, 4, 5. Do you see that? 6, 7, 3, 4, 5. So this line right here, line 4, it should be line 14, the one's being cut off. But this line right here basically overwrote the first two values to be 6 and 7. And that's why after we execute this line of code right here, b then becomes 6, 7, 3, 4, 5. And we could type that in. You guys can see that right here for yourselves. Six, 7, 3, 4, 5. All right, and then we do this last part. Where I say, okay, now, given that b is 6, 7, 3, 4, 5, now what I want to do is I want to say, okay, wherever b is greater, well, whatever this nonsense is, we'll just do it side by side. So here I'm saying, okay, wherever in b, where the b data elements are greater than or equal to 3, give me that subset. All right, deal. So I come back here, 6, 7, 3, 4, 5. Which elements are greater than or equal to 3? All of them are. In this case, I take a subset of all 5 of them. 6, 7, 3, 4, 5. I get them all back. So basically, 6, 7, 3, 4, this becomes 6, 7, 3, 4, 5. And to that, I subtract 5. All right, so let's do that here. Let me first write this whole thing here, just so you guys have it. All right, so I have this. Oh, that was nice. All right, so I have 6, 7, 3, 4, 5. So let's do the right side first. So the right side is going to be, it's going to be basically 6, 3, 4, 5 equals, all right? So 6, 7, 3, 4, 3, 5. This part right here, this part right here is 6, 7, 3, 4, 5. We're subtracting 5 from it. So this for now reduces. The right side now reduces to 1, 2, -2, -1, and 0. Okay, 1, 2, -2, negative. Oh, what did it happen? Sorry. Do it again. Sorry, losing my mind here. 2, -2, -1, and 0. Okay, and on the left side now, so this is what the right side is right here. This right side becomes that value right there. Now on the left side, I'm saying, okay, now overwrite all the values where B, remember, B is still 6, 7, 3, 4, 5 at this point. Overwrite the values of B everywhere where it's greater than or equal to 3. Well, that's every element. So what happens is 1, this position gets overwritten by 1, this position gets overwritten by, sorry, this position gets overwritten by 2, this position gets overwritten by -2, this position gets overwritten by -1, this position gets overwritten by 0, so B ends up becoming this value right here. And that is what's happening in that line of code with the vectors. Oops. And that's what's happening in that line of code with those vectors, right? And that's why the answer is this, 1, 2, -2, -1, 0. All right, so that's basically how it happens. That's what's going on over there. Now, so I mean, we'll trickle back to this. This is obviously the first time you guys are seeing this. We're gonna do this a couple of times, and slowly you guys will get the hang of this. But that's basically logically what's happening there, and we'll see this more. This you have to just practice in the practice sets, and I'll give you guys that, and we'll, when I post the practice sets, you guys will see that in the practice sets. So now we want to talk about we cannot do this lab because we're using something called a function called uniroot that requires something called user-defined function to work it. What is a user-defined function? A user-defined function in R is basically a function that the user defines. You define. It's a user-defined function. We've used functions so far. We use the C function, the REP function, the SEQ function, right? These are functions. These are predefined functions in R. You can write your own functions. And this is the technical body of a function right here, right? This is the definition. Let's go write our own function, and let's use it. Let's do a simple function here. In this simple function, I'm going to write a function that takes a number and simply multiplies it by 5 and returns it back out, right? So here, a very simple function I have, and this is the basic template of a function. So I have exmp equals function parameter x. Now, you don't need to have a parameter, right? You can just have a function that just simply does something very simple, like returns the value 1. So in this case, by the way, here, notice how this is in purple. Notice that's in purple. These are these are keywords. These are keywords, right? So here, this is my function name. You define that. You define that. You could be anything you want. It could be Superman, Batman. Here, I'll just use exp, for example. So you define whatever that function name is. When you process this, when you write your own function, you have to process it once, and then you can use it as many times as you want. So here I highlight the whole thing, I process it, and now you'll notice if you go to your top right window, another section pops up called functions, and here it's a list of all the functions you've written, you're using. So here you are. Your function exmp is up there. Now how do I use it? You just call it like every other function we use. If I do exmp, remember it's a function, so it has to have a close and open parenthesis. In this case, notice we left everything in here blank. That means there are no parameters for this function. There are no parameters. So when I type this in, I get the value 1. See? And I can do it as many times as I want. Pretty boring function. It pretty much returns the value 1. All right, so let's make it slightly more fancy. Let's let it take a parameter. And here again, I'm now putting a parameter in there. And that parameter is a variable. It could be anything you want. All that matters is how you use that variable. Right? So here, this is a way for me to input values into the function and have some logic happen. So what I want to do basically, like I said before, my slide, I said I want to multiply everything by 5, right? Yep, multiply everything by 5. So I'm basically going to do 5 times x, and I'm returning that within the parentheses. I didn't have to do that within the return. I could have done this outside, created a whole new other variable. That's t equals 5 times x, and I could simply just return t. So either way is fine, right? You could do the logic right in the return, or if it's more complex, you could do logic outside, and then whatever that final data container is, you could just simply return that. So here, because I changed the function, I need to reprocess this again. Right, so I reprocess the function, and now I will try using it. Notice now that I used exmp, I have an error. Why do I have an error? Because now the function requires a parameter, an argument, one argument. And that's how we got this error here. Listen, argument x is missing with no default. We didn't give any default parameter value, right? So you have to give a parameter value of some sort. So here, I'll give 1. I'll give 1. What's my answer going to be? We can see that from the logic. X will become x here. I put parameter 1 here. That means in the function, x will take on the value 1. And then in the code, t will become 5 times 1, which is 5. And then we return the value t, which is 5. So when I run this, boom. And the thing with the functions is you process them once and use them as many times as you want. So I already have it processed, and I'm using it. I'll do 5 in here. It gives me 25. I'll do 10 in here. It'll give me 50. I'll do 100 in here. Gives me 500, right? Because it keeps, all I do is it keeps taking the number I give it and multiply by 100. This is a very simple function, but in most of our cases, we keep our functions fairly simple for the logic we want to do. Functions are a great way to abstract away the code. So you can abstract any kind of code you want. I personally tend to not write that many functions. I just use them where I need them. In this situation right here, certain kind of functionalities that are built in that we want to use might require them. So that's why in this situation, I'll definitely I will use a user-defined function. So that's basically it. And so I want to show you something else, by the way. Let's say hypothetically I take the return part out right here, and then I process this. It'll work. There won't be an error, right? Now let me run this again. Notice what's happening. I have no error. I have no warning. I'm running the function, right? And it's working just fine. Like, for example, it's working fine because let's say I took the parameter out, then I'd get an error because the function's like, hey, you're missing a parameter. Cool. right? You're missing a parameter. But otherwise, it works perfectly fine. What's happening here? What's going on? Why aren't I getting an output? It's because you took out the return. That is the purpose return. That is the purpose that return serves in a function. Return, functions can do a whole bunch of logic, right? They can change data containers, right? They don't have to give an output. They don't have to give an output. But if you want an output, if you need an output, then you need to have that return, right? And this is how I get these outputs. And this is how also I can simply stick another variable to the left of it, and I can capture, see that? Created a new data container called res that will simply be the result from that function. And I can capture that value to be used later on in my code. That is the purpose behind the return. All right, that is the purpose behind the return. All right, so I think at this point now, we are ready to move on. Right, at this point, we are ready to move on. I guess before I give you guys another question to see how good you guys are with functions, here's a question for you. See if you guys can do it. Take a moment or two and see if you guys can do this. I will go ahead and break this down for you. I'll solve this for you. But at this point, just I would say pause it and try to solve this, right? Okay, welcome back. And I will go ahead and solve this for you. And I'll break it down. Let me basically do this using my trusty Excel sheet again. All right. So let's do this. Let's rock. So this example. All right. So here's the functions. And let's see if you guys can do it. All right. So what is this monstrosity right here? Right? No problem. Guys, when you see complex things like this, they look complex, but they aren't. You want to go inside out. Start off with the most inner function or data container you see. In this case, we have no data containers inside. We just have functions. So we start with the most inner function I could find. And it looks like the most inner function I could find is this one right here, a. All right, excellent. So look at the a function. Here's the open parenthesis. Here's the closed parenthesis. Okay. So I'm calling the a function with the parameters 1, 1. All right, a, 1, 1. So let me write this whole thing. For b to a 1, 1. 1, 2, 3. Excellent. So we start with this inner one, which is a11. All right. So what is a11? Well, we go to the function and it tells us. Firstly, notice that there's two parameters here, not one, x and y. Therefore, a, 1, 1 is implying that x equals 1 and y equals 1. Okay? So before we even start the code, x now has the value 1 and y has the value 1. Now I go ahead and I jump to line 3. In line 3, it looks like we have an if-else condition. So here, we're doing a little math and then a little logic. That's fine. Do the math and then we can check the logic. It's saying basically, is x plus 1, x plus y is what? 1 plus 1 is 2. Is 2 greater than 7? It is not. Therefore, we skip this part right here and go straight to the else. And else we're saying TOT is going to equal x times y, 1 times 1. So TOT is going to equal 1. And now we exit out the if-else statement And then finally, the last thing in this function is simply the return. We're returning TOT, so 1 is being returned. So A1 of 1 is basically going to give us the value 1. Is going to equal 1. A1 of 1 is equal to 1. So I'm going to come up here now, take this, and I will replace the A1 of 1 with, this is what we call simplifying it, with simply 1. And now I have this. Now again, I'm going to look for the most inner function there is, and it looks like it's B. And here, B has my open parenthesis and my closed parenthesis, excellent. And within it are two values, 2 and 1. Fantastic. This means that I'm doing B2, comma 1, and it has a parameter A, which is going to take on the value 2. It's by position, guys. So because A is the first value, A is the first parameter, the first value goes to A. And this B is the second parameter, the second value goes to B. So now B equals 1. So A is 2 and B is 1. This is a simpler function. I jump down here. TOT is going to equal simply A times B plus 10. So A times B is 2. 2 plus 10 is 12. So TOT is going to equal 12. And I'm now going to return that TOT. So the value 12 gets returned for B of 2 of 1. So B 2 of 1, 2 comma 1, sorry, is going to be the value 12. Sweet. So I come here again. Let me just bold this so you guys can see this, how we minimize this. And so now I take this value right here, and I minimize it. So B2 of 1 now, I replace the B2 of 1 with the value that gets returned by it, and that is 12. And now we come back to A. Now we come back to A, right? And again, A4 of 12 is going to be simply X will equal 4, and Y will equal 12. And let's run through it. In line 3, X plus Y is X plus Y greater than 7? Well, X is 4, Y is 12. X plus 4, 4 plus 12 is 16. Is 16 greater than 7? It is. Therefore, TOT will be 4 plus 12. So TOT is going to be equal 16. All right. The else part is skipped. I come here to the return, which is TOT. So the value 16 is being returned. Excellent. So basically A 4 of 12 gives me the value 16. And I am done. I have nothing else to minimize. So the final answer is 16. Final answer is 16. So that's basically how you would break down this right here. That's how you basically break down that answer right here. So the answer became 16. Congratulations if you got it. If you didn't, go back and just do it again. All right. And now, ladies and gentlemen, we are ready to tackle our lab. All right. So for lab 1, if you remember, right, we're going to go all the way. Let me go all the way back. How we started this journey. For lab 1, we wanted to calculate we basically want to calculate your compound return. Now, look, some of you guys are seniors, but you guys know what your packages are. And I know COVID is going around and everything's being screwed up, but you guys know you guys can basically figure out what your package is through your friends and what your major is, et cetera, and the jobs you'll be applying for. So I will be doing it for a typical Bates student, and as of I think the package for most of the Bates students, they go into consulting, and the first year salary for a lot of these consultants tends to be around the same thing, around, let's say, 65,000. So I have the situation where I have a freshman I have a student that paid 11,000 throughout their 4 years at Rutgers. 11,000 freshman, sophomore, junior year, senior year, etc. Right? And they basically now have this salary of they're going to get the salary of 65,000. Well, if they paid 11,000 for 4 years and they're going to get this payout of 65,000, right? What is their compound return going to be? From this example right here, you should know that 65,000 is greater than this number. Therefore, it's safe to say that the compound return for my fictional bait student will be greater than 10%. Because at 10%, it would be this, right? So because I'm doing it for 65,000, their compound return needs to be logically greater than 10%. Okay? Obviously, everybody has different numbers. What I want everybody to do is I want everybody to do my example first to make sure your code is working, and then I want you to plug in your numbers. And I want you guys to basically, you guys to have an idea of what you're going to be making. You guys do know what you're paying, and I want you to calculate back out and calculate your compound return, right? Your compound return for your investment. And that, now you've quantified exactly how much your tuition, your education was worth from an investment point of view, right? And the cool thing is that for the lab 2, we're going to then compare that your compound return for your education with the actual compound return you would have made from the market, hypothetically from the market. I mean, we have to make some assumptions, but it's fun. So I'm going to do this 3-way, guys. I'm going to do this 3 ways. I'm going to do it what I call the barbaric way, using a for loop. I'm going to do, the semi-barbaric way. I'm going to recreate the for loop logic, but this time I'm going to do vector mathematics. And then I'm going to do it the completely right way, which is using the function I call, a nifty little function called the uniroot function. And the uniroot function is basically a simple optimizer in R. It's a very simple optimizer. It obviously can get very, very complicated. The optimizers you have access to in the world of R are obviously anything that exists in the mathematical world, statistical world, you have access to. We're just going to, for our purposes, we're just doing a simple optimization. So uniroot will work perfectly fine for us, right? Perfectly fine for us. So let me start with the barbaric way, right? Oh, I didn't write the barbaric way. Okay, I just jumped straight into the, in my slides, I just jumped straight into the actual, the right way to do it using uniroot. So I will, in my R code, I will do the barbaric way and semi-barbaric way, and then I'll jump into the slide. So let's do it the barbaric way first. All right. So in my code here. All right. All right. So what do I know? I know that I have I need to basically come to 65,000. I have an equation, R. Let's start with a rate. I have a rate. So let's start with the 0.1, the 10% from our original example. And I'm going to use some variables to keep this, to minimize the amount of typing I have to do. 11,000, right? So that's the payments basically. So I'm going to set up my equation. So I have basically, I'm going to have this equation that's going to be basically P times 1 plus R to the power of 4. And I'm going to set up my whole equation. So basically my freshman year, sophomore year, junior year, senior year. Boom. Process this. Oh. Excellent. So I started off with my original equation. All right, so from here, what I want to do is I want to use a for loop to get this line 141. I want to keep changing R so that I can get line 141 to be as close as possible to 65,000. And I'm going to use a for loop to do that. All right, so at this point, this is we're reaching the hour and 20-minute mark on part B. So this lab is going to cross over to part C. So at this point, I will end this video, and we're going to pick this up right at this point in part C. All right, guys? All right, bye-bye.